Section 1.3 is on voltages. Voltage is the energy transferred per unit charge flowing through a circuit element. So the standard unit of voltage is the volt, usually capital V, but because this again is another rate similar to current, it is joules per coulomb, or J/C. So voltage is measured across the ends of a circuit element. Remember that current is a measured charge through the element, through that cross section. But voltage is measured in terms of what the difference between the ends, okay, the differential there. So energy is transferred when charge flows through an element having voltage across it, all right? The transfer depends on several items: charge, polarity of origin, and the direction of the movement, right? So voltage is assigned a polarity to indicate the direction of the energy flow. And we'll draw a few diagrams to represent the cases where the energy is absorbed by the circuit element, which might, for example, represent resistance, which is used to produce a heating element, a coil type thing. When energy is supplied by a circuit element, for example, a particular source of energy, a voltage source, for example, would be supplying the circuit, so be supplied by that element. All right, so if we turn over to page 7 in that box, we'll illustrate the differences between the absorption and the delivery or supply or the supply of energy relative to voltage. So the first scenario we'll look at is the case of energy absorption, or the fact that energy is being absorbed. So, and we're doing this for an arbitrary circuit element. So for that arbitrary circuit element, we'll just draw a very simple box diagram with two terminals here, one on top and one on bottom. And let's represent arbitrarily that the top terminal has polarity plus, and the bottom terminal has polarity minus. The representation of energy absorption, it follows from two possibilities. Number one, either you have a positive charge, net charge here, all right, that's flowing from positive to negative polarity through voltage polarity. That's a representation of absorption. Or you could have a negatively charged flow coming through the negative polarity of the circuit elements, okay? Where again, these are the voltage polarities. Okay. So that's an indication of how energy would be being absorbed, okay? It depends on how, if you have a net positive charge flowing into the direction of the positive the positive polarity of the voltage, then you're absorbing, or you have a negatively charged net flow coming through the negative polarity of the voltage, all right? So energy delivery, or energy is supplied, if it's the other scenario. Okay. All right, so again, this is, we'll draw the same representation of the circuit element. The top terminal being the positive polarity, negative as the bottom. If you now have a negative charged coming through, the negative charge is coming into the positive polarity of the voltage for that circuit element, then energy is being supplied. And the same thing is if the opposite sign, so the plus charge is coming in through the negative polarity of the element, again, they're opposing. So you see that the sign of the charge, if it's opposite of what the polarity is of the voltage, you're representing energy being supplied. If they are matching, in other words, positive to positive here, negative to negative, they're coming in there, then energy is being absorbed. So that kind of makes some sense here, that you're absorbing more of negative or absorbing more of the positive, where here they're opposite, so the energy is being dissipated, okay? Again, with current, we can have reference instead of directions. We'll have reference polarities. Okay, we had reference directions for current, and 1.4 we look at reference polarities. Okay, so if you don't know voltage values and polarities, you can assign them. Okay, and choose the reference polarities arbitrarily. All right. So let's look at this example in figure 4, which is circuit 4 here. And you can see we have another diagram of 5 arbitrary circuit elements, and we are representing the voltages with these variables V with subscripts for each of these circuit elements. All right. And you can see that we've assigned reference polarities across these 3 here, A, C, and E. We have the top terminal being positive and the bottom negative. Across the top row here for B and D, we have the leftmost terminal being negative and the rightmost being positive, okay? So in this example, if this is again, is just signing a reference, but if we were actually to measure the polarity of this particular circuit element C, and we determine that the voltage is negative 5 volts, all right, then what we would know, because this is the assigned polarity here, is that that the 5 volts in magnitude actually is reversed in the polarity, so that in reality we should have had the bottom being the positive and the top being the negative. It's you know, there's nothing wrong with the magnitude, but the fact that this is negatives means we have the polarities actually reversed, all right? That's very similar to what would happen with the current directions, remember, where if we turned out we had a negative ampere, then that must have meant that we've got the current direction actually reversed. So the same thing applies here in terms of your assigned reference polarities versus what you might measure them to actually be. Remember that DC voltages have constant values and AC voltages change in magnitude and alternate in polarity with time, very much like we saw with current, right? So some examples, for example, with a DC voltage, you might have something like this, 10 volts, standard battery, a 10-volt battery has the same value and polarity through the same, no matter what the time is, versus if you had an AC circuit where you're looking at voltage changing in magnitude and polarity by a cosine function, right? So this is just supplying a constant voltage, and then again, this is an example of it changing in polarity and magnitude. Again, voltage is the energy that you're transferring as the charge flows through the circuit element, the energy that's being transferred. And you can do subscripting to represent the flow if you want in terms of the energy transfer. For example, double subscript notation like we had for current can be used for voltage. In this case, what we've represented as a resistance here, and there's voltage through both of these resistances. The top terminal is labeled A, the bottom is B, but notice we have the sign differences. The A is the plus polarity, B is the negative. And if that is the case, then we would index the voltage VAB, all right? Another way to think about it is the first subscript here is matching the positive polarity, and the second one is matching the negative. And so here, clearly, if we index it VBA, then we automatically are saying that, oh, B must be the positive pole and A must be the negative one, right? So it just means that you wouldn't have to put plus and minus deliberately if you knew what the indexing was, all right? This above representation using subscripts is very common in American circuit designs, but sometimes you will find other representations, which I'm going to show you the next page, especially in European circuit design. Sometimes you'll see them use arrows rather than subscripts, right? So if we turn over quickly to page 8, at the top of page 8, you'll see exactly what we're referring to. Is the same representation of these two resistances. Top terminal is A, bottom terminal is B, but they use arrows here. And the direction that the arrow is pointing to is going to be your positive polarity. So in other words, it's pointing to plus and it's coming from minus, or it's pointing to plus here and coming from minus, all right? So it matches up exactly to what we just had a minute ago, but rather than using pluses and minuses, you may see them with arrows, but the arrow is of it that is always pointing at the plus, the positive polarity, okay? Also, let's talk a little bit about switches, because switches are very important to control current and therefore voltage as well. So current through an ideal switch is 0 when it's open, all right? And the voltage across the switch is determined by the rest of the circuit, all right? So it's very important to realize that if you have an open, when a switch is open, there is no current, but there is voltage flowing across that switch. When the switch is closed, all right, the voltage becomes 0, but the current is now flowing through the circuit. So it's just important to understand the differences between what we mean if you had a switch like this and it's open, all right, and we were looking at 2 terminals there. What we're saying is that when the switch is open like this, we have no current flowing through between A and B, but there could be voltage as determined by the rest of the circuit, right? But when you close it, when this becomes closed, then you would have no voltage across that, but you would have current flowing, right? Okay, so let's look at an example, example 5. Again, to finish out this discussion, suppose the voltage across a circuit element is indexed VAB equals 20 volts. So we're using the American style representation of voltage with indices, and we can immediately tell what that means in terms of drawing it. For example, if we were to arbitrarily draw the circuit element and label, let's say, the top terminal A and the bottom one B, we know something immediately because we've indexed it VAB equals 20 volts. We know this must be the positive polarity and that is the negative polarity, again, just for the way we indexed it. So it's reading on, it says a positive charge of 2 coulombs moves the circuit element from terminal B to terminal A. So again, we have a positive charge of 2 coulombs, and it's moving from terminal B up to A, all right? All right, so, and then it asks us, the question is, how much energy is transferred? Is the energy supplied or absorbed by it? In other words, which is, which scenario, one of 2 scenarios we just talked about in terms of whether the energy is supplied or is absorbed. And of course, remember, voltage is the energy transfer rate of joules per coulomb, right? So, so in this particular case, what we really have here is if voltage is joules per coulomb, right? And we are given that the voltage is 20 volts. That says we have 20 joules per coulomb, correct? And if we then multiply that by the positive charge, which was being moved through the circuit element, which is 2 coulombs, then what the amount of energy we're really transferring, if you multiply those 2, notice the units of coulomb go away, we really are transferring 40 joules, right? Oops, sorry. So the voltage through the circuit element, the energy transfer rate is 20 volts, and we have 20 coulombs to transfer. Therefore, the amount of energy that's going to be associated with that transfer is 40 joules, right? So it's just simple product there, those 2 terms. So, and again, we'll just reiterate that what we have is a positive charge flows from the negative voltage polarity to the positive voltage polarity So therefore, we know, okay, energy is supplied in this case. it'll be delivered to other parts of the circuit for which the circuit element is connected to, right? Is supplied by the circuit element. Okay. Either the circuit element is absorbing it, which would be the case, for example, if you're trying to have a heating element and you want to absorb more energy so it gets hotter and hotter, like in a hair dryer having different settings, or are you trying to maybe deliver the energy somewhere else into the circuit? Okay. So in this case, we are delivering it or we are supplying. So delivery or supply means the same thing, but we're definitely not absorbing the energy. All right. Again, the positive charge of 2 coulombs is coming into a negative polarity of this voltage polarity of the circuit element. So energy is going to be dissipated. Okay. And then the next section, coming up in the next lecture, we're going to look at power as another very important component, which represents uh, the, um, the product effect of volts and amperes.